Hello and welcome to this video about vector spaces proofs. In this video we'll prove that any set Rn where n is finite is a vector space by proving all of the axioms. I really should have done this video first, but I got it jumbled up, which can happen with a large textbook. I can represent any of these vectors with a row vector, which can easily be changed into a column vector for all of these exercises. So now to prove that it's a vector space, we'll start with the first axiom, which says that the sum of any two members of the set will also be in the set. I like to write my vector variables in red to make them stand out. We'll define these two vectors to be these finite row vectors. It's good enough to represent it in dot notation. I don't have to show every element in the row vector. I've used a weaker red to display it called tomato in HTML. I've also used square brackets to distinguish them from function operation brackets. So now we'll add these two vectors together. And this is how we add row vectors together. We add each element in the same location and place the sum into this same location in the new row vector that we're making. And finally, this is in the form of a row vector, and so is a member of Rn. This completes the proof of the first axiom. Now to prove axiom 2, that the product of a row vector by a scalar is in the set. The scalar is the type of number we'd use for any element in the row vector. So we'll multiply this scalar by the vector x. This causes every element in x to get multiplied by this scalar. And because it's of the form of a row vector in Rn, then it's a member of Rn, and this completes axiom 2. And now to prove axiom 3, which we'll do on this page. We'll have to prove this commutativity property, which is a type of symmetry for this operation. So we'll start with the left-hand side and expand it out using row vector notation. Then we'll add the two vectors together to make one vector. Then we'll swap each element like this, so that the element of y comes before the element of x. Then we'll separate this vector out into these two vectors like this. This is a legitimate step in this proof, because we don't have to simplify expressions all the time, but we have to do whatever the proof demands. And finally we can substitute the original vectors back in for x and y, proving this axiom true. Now to prove this fourth axiom. It's associativity that allows you to swap the brackets like this, which is essential to prove painfully obvious things like that 0 multiplied by any vector gives the 0 vector. So we'll have to define z to be this row vector because we haven't defined it yet. So starting with the left-hand side, we'll substitute in all the row vector versions of these vectors. I like to use different colours and bracket shapes so that the expression won't be so confusing to look at. We'll add y and z together first because they were in brackets. Then we'll add these two vectors together to get this one vector. Then we'll separate out the z vector. Then we'll separate the vectors x and y. We separated them last so that we can put them in brackets. Then finally we can substitute the vectors back in as single variables or in red notation, because I'm using red to write the variables with. So now to prove that the 0 vector exists in Rn, with this definition, that adding it to any vector in the set returns the vector unchanged. So in order to prove it, we'll set the 0 vector to be this vector, which is a row vector of n zeros, and then we'll show that it satisfies this definition. So we'll start with one of the addition expressions, which is x plus 0. Then we'll add these two vectors together. Then all of these zeros will cancel. And then we'll get the vector x all by itself. And we can do a similar thing with the 0 added to the other side, and so this completes the axiom. Now to prove axiom 6, which says that there exists a negative for every element in Rn. We can prove this by showing that it's true for an arbitrary x. We'll set the negative of x to be equal to this row vector, which contains the negative of every entry in x. Then we'll show this to be the negative of x. So we'll start with the left-hand side and substitute in the row vectors for these variables. Then we'll add them together using row vector addition rules. And they'll add together to make a vector of zeros, which is equal to the 0 vector as we've defined it before. And we can then similarly prove it for the addition of the negative on the left-hand side of its positive, and thus we've proven this axiom. So now to prove this axiom, which is a distributivity axiom, we'll substitute in the row vector forms of these variables, and we can easily expand the brackets using the rules that we know will work for these row vectors. Then we can substitute the variables back in the way that we usually write them, and thus we've proven this axiom. Now to prove this distributivity axiom, which is very different to the first one. This time we're distributing the scalars. We haven't defined b yet, so we'll write it out again defined with a to be a real number. So we'll start with the left-hand side and substitute in the row vector for x. And we'll multiply the row vector by this real value in brackets. Then we'll expand all of the brackets for each entry in this row vector. We can then easily split this row vector up into a sum of two row vectors. Then we can factorize the common variables from each of these row vectors. And finally we can write the right-hand side of this axiom equation, thereby proving this axiom. Now to prove this multiplication associativity axiom. We'll substitute in the row vector for x. We'll multiply every entry in this row vector by the amount in front of it. We'll swap the brackets in every entry in this row vector. We'll factorize this vector, placing the variable a in front. We'll factorize it again, placing b in front, with brackets showing that we factorized a first. Then we can substitute the original variable for x back in, and so we've proved this axiom. And now for the final axiom, that multiplying a vector by 1 leaves the vector unchanged. We'll substitute the row vector for x into the left-hand side of this axiom equation. Then we'll multiply every entry of x by 1. This leaves every entry of x unchanged, which gives us x unchanged back again, which proves this axiom. So we've proven all of these axioms, so we can now say that Rn is a vector space. And now we can prove these two difficult theorems very easily for the vector space Rn. We'll start off with this theorem. We'll start with the left-hand side and substitute this row vector in for x. Then we'll multiply every entry in x by 0, which causes every entry in x to be 0, which is the definition of the 0 vector, thus proving this theorem true for Rn. We can easily prove this difficult theorem too. We'll start with the left-hand side and substitute in the row vector form of x for x. Then we'll multiply every entry in x by -1. This gives us the negative of every entry in x, which is the definition of the negative of x. So we've proven this theorem true for Rn. It doesn't prove it true for vector spaces that have an infinite number of entries, so that we still need the other forms of these theorems for infinite vector spaces. So I hope that you've found this video to be helpful and educational. Please click like and subscribe if you did. Please leave some helpful thoughts and ideas in the comments. Feel free to share this video, and thanks a lot for watching.